All right, let's get started here. So we're working on this week here. Last week you started Hypothesis Test Part 1. It was a PDF form file. That way I was able to pretty much lead you by the hand through all the steps of a hypothesis test. And then we continued on with that in Hypothesis Test Part 2, but it did less prompting. And then when you get to Part 3, you won't have any prompting at all. You'll just have a great big empty box to fill in. So that's the way we're going to approach the ones we're going to work on today. Now, what you got to remember in Part 3 is you got to check conditions because there's no guarantee that the conditions will always be met. So you got to check them. So without further ado, let's take a look at some practice problems here. Now, what I will do is, now here's a form, a little template. If you're still kind of learning, starting, you don't quite remember all the steps, this little template is handy. And you might be wondering, now where could I get one of those? Well, one possible place is if you go into my stat lab, and let's suppose that, let's go back here to the main menu, and I go to external links, files from the live lectures, and this was the lecture for last week, and here's a template for all hypothesis tests. So this is the document we're looking at now. It just reminds you of the steps. Now here's the questions that you want to always get in the habit of asking yourself on every exercise you do. What were you being asked for? Well, you'll notice in this first one here, they're not asking you to construct a confidence interval or calculate a sample size or to calculate the probability of one randomly selected being an interval. They're asking you to test a claim. That's how you know it's a hypothesis test. And then what type of data is it? It's either quantitative or it's binary. It's one or the other, so you've got to recognize which it is. And then, as the focus of today is, we're going to make sure we check the conditions. Now, you should already be good at this because they're the same conditions that apply to confidence intervals. So if it's quantitative data, of course you got to have a random sample, of course. But after that, either your population that you're sampling from is normal or your sample size is at least 30 or more. Now, if it's binary data, it's entirely different conditions because it's entirely different data. For starters, you don't say if the population is normal because that doesn't make sense for binary data. The population of binary data has no shape, center, or spread. And we've talked about that before, particularly in chapter 8.2. So there's only one way to check the conditions for binary, and that's if the sample sizes are large enough. But what's a large sample? It's not the same rule as for quantitative. It's not 30 or more. It's an entirely different rule. We have a little test. And that test, well, let's go back to that those files we were looking at. Here's the formula sheet for the final exam. Let me put that to the desktop. And then let me open it up. And there's that little test right there. By the way, so you can see what the formula sheet's going to look like on the final exam. Formulas from the first midterm. Then, of course, what you see here. And formulas after exam 2, there aren't any because all we're doing is using the built-in functions on our handy little calculator. But anyway, so it's got to pass this test in order for the conditions to be met for binary data. By the way, there's another rule that's a little more intuitive because when you take a random sample binary data, you go through that random sample and you separate it into 2 piles. In one pile, you're putting the ones that are in the category of interest because it's all categorical data, and whatever isn't in that category goes in the other pile. So you have two piles. Now, if you look at both piles and they both have at least 10 items in them, a count of at least 10 in each, the sample size is big enough. Most people find that's a lot easier to remember than this formula. But of course, you don't have to remember the formula. It's on the formula sheet. All right. So here we go. This will be our little template we do. So I'll have that up there. Let me scoot this off to the side, and then we'll look at a scenario as we go through this process. Let's see, we don't need that anymore there. We can go ahead and get rid of this calendar. Okay, let me resize this, as we only need to look at one thing at a time. And so what we got going on here. So they're telling us 37% of all Americans use only a cellular telephone, no landline. A random sample of 32 20 to 24-year-olds who live on their own was taken. And 16 of them use only a cellular telephone, no landline. So for A, this is all we're going to focus on for now. So let me scoot this up. Is there sufficient evidence to support the claim that the proportion of all 20 to 24-year-olds who live on their own use only a cellular telephone with no landline? Is that proportion larger than 37%? Use a significance level of 1%. So first of all, notice the key words. Is there sufficient evidence to support the claim? Now that is a hypothesis test, because you never saw anything like that before we got to hypothesis test. But whether we go along with the claim or we don't, we're testing hypotheses. So hence, that's what we're doing. And so we know it's a hypothesis test. Our next question is, what type of data is this? What are we doing to each of these 20 to 24-year-olds? Are we measuring something, or are we putting them into a category? We're putting them into a category. Either they're in the category of using only a cellular telephone with no landline, or they're not in that category. It's binary data. All right, so now that you know it's binary data, why don't we go over here and start filling in our little template here. And we'll use a template because you might have, still be struggling to remember the steps, but you just keep reviewing it each day till you do remember the steps. So let me get my annotation pen here. There we go. So the first thing you put after you write out your null hypothesis is your population parameter. Now, if it was quantitative data, I'd put the population mean. But it's binary data, so I put the population proportion. And you always have the equal sign, always, always in the null hypothesis. Never put the inequality in the null hypothesis. And then what's the hypothesized value? Okay. Well, up here that we have this population proportion stated up here, that it's 37%. What's being claimed up there? Now you got that. Now copy down everything except for the equal sign. That's what you always do in the alternative hypothesis. Just copy down everything except for the equal sign. So that makes the alternative pretty easy to do, because all you have to do is figure out which inequality. So read carefully, and what is it they're interested in? Larger than 37%. All right? And that's our alternative. If it's not equal, then our other alternative is that it's larger than 37%. Now that you've gotten that far, let's go ahead and put in our significance level they gave us. That's the symbol for significance level. You can write it in decimal, or you can write it as a percentage. But next thing we should do is let's make a picture of what would be happening if the null hypothesis is true. Now we're talking about binary data, and so we want what would be true about the distribution of all the possible sample proportions we could ever possibly get from repeated sampling if the null hypothesis is true. Well, you know, these cluster around the population proportion, and that is equal to 37% if the null hypothesis is true. So I know 0.37 be right smack dab here in the center. Let's make it more like a 3. So that's a simple sketch to make. If this is the population proportion, this is always the sample proportion. Whatever number that's in these two hypotheses is always the number in the center. Always, always. Okay. Now let's run this through our head. Now this is important for you to do on every exercise, so you start to understand and remember the logic behind this. What you got to make sure you're clear on is that if I get a sample proportion, and let's suppose it's larger, but just a little bit larger, that's not unusual, is it? You say, oh, yeah, I didn't expect to be right on the money, but if it's just a little bit larger, that's not unusual. I mean, that's the sort of thing I'd expect to happen if the null hypothesis is true. You expect your sample proportion to be close to the center. So the closer you are to the center, more likely you are to go with the null hypothesis. But what if I'm farther? What if I'm really far away? So the idea is the farther above I am, the stronger the support and evidence for the alternative. Now, yeah, the population proportion is probably greater if I got a sample proportion way up here. To be that far above or farther is very unusual. In fact, to be given by the area under this curve. Because you calculated areas under this curve in chapter 8.2. All right, so you got the big picture. All right, now let's go over to our calculator and deduce which function to use. So I go over here and I press stat, go over to test, and so you notice you got these 6. Now you see the ones with the 2 in front? We won't get to those till next week. So set those aside for now. Now z-test and t-test, those are for quantitative data, and this is binary. So throw those out. Well, you've got only one left, and that is one prop z-test. So we should, it's always a good idea for you to do this, document your work. We're going to use one prop. That's a good strategy on an exam. In case anything goes awry, your teacher knows at least you knew the correct function to use on your calculator. Oh, wait, there's something we haven't done yet that we should always do. We got to check conditions, don't we? Are the conditions met? Well, let's see. We took a random sample, so that was taken care of. But what's that other thing we have to check? Oh, essentially, we need to verify that this sampling distribution is normal. Well, our sample size needs to be large enough, and so it would have to pass this little test. So we want to know if I take n times p times 1 minus p greater than or equal to 10, does that pass? Now, you might be wondering, now which do I use? Do I use this 37% for here, or should I use my sample proportion, which is 16 out of 32? It's considered okay to use either. I've seen it done both ways. Me, I always tend to use the sample proportion because I always say, well, who knows? Maybe we'll end up rejecting that this is the case. But, you know, I'm not going to mark you down one way or the other. Now, our sample, but you notice on your formula sheet, it has the p hat there. So I'm going to use the p hat. Now, so we've got a sample size of 32, and our p hat is the 16 out of 32. which happens to be 0.5, and 1 minus p hat. And so let's calculate what that is. So I'm going to press second quit to get to the home screen here. And we'll put in 32 times, I'm just going to go ahead and punch in the whole fraction, even though I could be putting in decimal, and 1 minus 16/32. Let me double check. Yep, looks like I punched in correctly. And uh-oh, that's equal to 8. What do you think about that? So this is equal to 8, but that's less than 10. You know what this means? The conditions are not met. Well, I'll be darned. Could something like this happen to you on a homework exercise or an exam? It could. So always check conditions. You'll see, but even though they're not met, we'll just say this. If the conditions had been met, in other words, we would need to have a larger sample size, this is what we would have done. Dot, dot, dot. And so that way you can see everything else. So that's what I want you to do. Don't think that, oh, conditions are met, I'm just going to leave it blank. Well, here's why you don't want to do that. Because you'll be missing out on a valuable opportunity to beginning practice on hypothesis tests. Because the purpose of this is you're running these concepts through your head. So that's what I'm doing here is I'm reminding you of the concepts you should be thinking about. Because once you understand and remember the concepts, then it's much easier to do hypothesis tests after that. Because every step makes logical sense. You know the reason behind it. And you're able to remember it far, far better. So never leave it blank. But also leaving it blank, here's another problem. What if you had just miscalculated here and you had mistakenly thought conditions were not met when they were? Well, if you left it blank, you'd be missing out on a lot of points, especially if it were an exam question. It's not worth taking a chance. Another scenario that will get you into trouble is that it's true that if the conditions are not met for this one, then it's also true that they won't be met for the a follow-up confidence interval, like we see right here. But when you follow up with a sample size, the conditions are always met for a sample size. You can never skip this. So if you skip this one thinking the conditions weren't met, you'd be missing all those points. So why are there no conditions to be met for this? Because it's how large a random sample would need to be. And the idea is whenever you calculate these are really large samples. And you'll know for both binary and quantitative data, when you have really large sample sizes, the conditions are met, provided it's a random sample. So you don't have to worry about, you always do a sample size calculation because they're always really big sample sizes. So, moral to the story, never leave it blank because it could cost you a lot of points. And so don't take a chance. And plus, you're missing out on all that valuable practice. And you wouldn't want to do that. All right, so let's go ahead and do the work. Now, the nice thing is by the time you've done this much, you've really done a lot of the work because OneProp Z-test is going to prompt you for the inputs it needs. So we'll just go over here. I'll hit the clear key and we'll press Stat. Go over to test, and like we said, we're going to use OneProp Z-test. Go in there, And so P subscript 0, that's your hypothesized population proportion. See that little subscript 0? Think of the null here. So what number did you use in the null, which has to be the same as for the alternative? That's your 0.37. So enter that in, 0. And be sure and enter it in its decimal format, not 37. And then we'll go and enter the information from our random sample. Now from the sample size of n, how many were in the category of interest? 16. So that's what your x is. And n, your sample size is 32. Our sample size, that was too small. Oh, and notice it's 32. So if you thought a sample size of at least 30 was big enough because you were confusing this problem with quantitative data, you would have mistakenly thought the sample size was large enough. So this is a good example of why it's a different rule. You know, saying 30 or more is not necessarily big enough for binary data. Now let's go down here, and we need to highlight the greater than and hit enter to select it. So notice that's pointing the same direction as this one. And once you have that, highlight, calculate, and hit enter. Now what's super important is that you understand these numbers. So this is what your alternative hypotheses should look like. So our little p, they're representing as prop for proportion. Yep, it's going the same direction. Now make sure you understand what this test statistic is telling you. So let's write that down over here, and then we're going to put it in our sketch to make sure you understand it. Now, whenever I have students that are having trouble with this, I usually invariably find they are not making their sketch. So don't you be one of those, 1.52. Now what does that mean? That means our sample proportion, look, they calculated for us. There's our p hat. Notice that 16 divided by 32 is 0.5. Well, where is 0.5? I know it's to the right here, but how far to the right? It is 1.52 standard errors. That's 1.52 of these tick marks. So it's right there. That's where our sample proportion landed, our p hat. This p hat right there of 0.5 landed right there. 1.52 standard errors. Now, how unusual would it be to get a sample proportion this far above or farther? Oh, that would be this area here. So you always shade in the area away from the center because that tells you how unusual it is. So that area right there, that's your p-value. Now, when you do your work, especially in part 3, there's something I don't want to see. I don't ever want to see you write the p-value like this with a p. Wouldn't that be confusing? We're already using the little letter p to represent the population proportion. So think how confusing your work would be if you're using a p here and you're putting a p for this. So I don't care if that's what the calculator shows. Don't you dare do that. You're always going to write out p dash value like here and like I did right there. So your p-value is 0.0639. So that's 6.39%. Now, this is what I want you to do when you interpret this. What makes this easier is having this sketch. So your p-value is this area. Now, that is equal to 6.3%. Now, how do we interpret that? There's a 6.39, excuse me, I think I said something else, 6.39% probability of getting a test statistic this extreme or more extreme if the null hypothesis is true. Now keep practicing saying that because you know I'm going to test you on it because it's one of the most important definitions for you to get right. So practice saying it correctly so you don't garble it up. All right. Now, why it's important to know that is so you can see that the farther away you go, the smaller and smaller this area gets. And of course, the farther away you away you are, the stronger the evidence to support the alternative. So how far off to the right do you have to go before you have enough evidence to support that? Well, when this area to the right shrinks down because you're going so far to the right and that area gets so small, it's as small as your significance level or smaller. Right? Oh, this area would have to get as small as 1% or smaller in order for me to go with this. And you'd probably notice that, gosh, why did they use 1% instead of the usual 5%? Well, they got some explaining to do. Now, as you'll learn, this significance level is actually the probability of a type 1 error. Oh yeah, here's another thing we should do. Whenever we set up our hypotheses, we should run through our head what a type 1 and type 2 error are, especially if this is not 1%, because they're saying one type of error is much worse than the other. Well, we better know what the two types of errors are then, huh? So this is how it goes. Now, we're either going to go with this hypothesis or this hypothesis. It's the only choices we have. And of course, since we're basing our decision on a random sample, there's always a small probability we're wrong, just due to sampling error. So that's what type 1 and type 2 errors are. It's coming to the wrong conclusion, even though you did everything right, you're only wrong due to sampling error. So it's not your fault, it's just the price we pay to use inferential statistics. So let's suppose that now if you do this before you ever get your p-value, that's great, because you're saying, hey, I don't know what's going to happen. You know, I could get a p-value this small or smaller, and if I do, that's because I was so far away, and that's evidence to support the alternative hypothesis, so I'm going to go with this one. Now, I could be wrong due to sampling error, and you know what type of error that is? Why, that's a type 1 error. I wonder how you would ever remember that. You go with the alternative hypothesis, and you're wrong due to sampling error, it's a type 1 error. Now, the only other way you could be wrong is if you went with the null. And you did that because you had a big p-value, like we have here. Notice our p-value is bigger than our significance level. So we're going to do what we're supposed to. We're going to go with the null hypothesis. But we could be wrong due to sampling error. And is that a type 0 error? No such thing. It's the other one. Oh, that's the type 2 error. Now, the significance level is actually the probability of a type 1 error. Oh, well, they made the probability of a type 1 error really small. Well, why would you make that probability so small? Because they're saying a type 1 error would be far worse than a type 2 error, which is going with this one and being wrong. Well, the problem is that when you make this probability of a type 1 error so small, you skyrocket, make much bigger the probability of a type 2 error. So you better have a darn good reason why is a type 1 error so much worse than a type 2. Okay, so keep running those two types of errors through your head because it takes practice getting used to that. Now let's see here. Let's get my digital pen here. And so our p-value is big, 6.39%. And that's much bigger than our significance level of 1%. So our p-value is bigger. So how we state that conclusion is we do not say that we accept the null. That's a no-no. You say we failed to reject the null. You got no evidence against it. Okay. Another way of saying that is there. So stating in conclusion, I'm not going to write this out, but I'll say it in words. So there is not sufficient evidence at the 1% significance level to support this alternative hypothesis that this population proportion is greater than 37%. That the proportion of all of these 20 to 24-year-olds living on their own that use a cellular telephone, we just can't support that that was larger than 37%. Now, what we want to do is follow up with a confidence interval. And if you wrote out which function to use, that makes it easy. Just replace the word test with int, and you know what to follow up with. 1 prop z int. In fact, I want to leave this work up here. Let's just go over to our calculator over here. Because the beauty is, all this information is still in here. Oh, another thing I want to show you. If I go to stat test, and then let's go back into the 1 prop z test that we were just in before. Did you know that if you go down here, instead of highlighting calculate, you highlight draw and hit enter, it is going to draw this very same sketch for you. See, doesn't that look identical? And unfortunately, it uses P for p-value, but that's the area, and there's your test statistic. So this is a nice way to verify you're drawing your sketch correctly. Now, let's press stat, go over to test, and if I replace the word test with int, we want to go to 1 prop z int. You've used it before. So let's go in there. But now we're following a hypothesis test. These values are already entered in for you. All we have to do is punch in the confidence level, and I'll just give that to you. It's 98%. So put in 0.98. Highlight calculate, hit enter. So we're 98% confident that our population proportion of all 20 to 24-year-olds who living on their own, who use only a cellular telephone, no landline, is somewhere between 29.438% and 70.562%. I want you to think long and hard about the width of this interval. Is that a pretty wide interval? It's outrageously wide. And why is it so wide? Well, look at our sample size. Is 32 a very big sample size? It wasn't even big enough to pass this test. So this is what you're going to find. If your sample size that's being used for binary data isn't even big enough to pass this test, you can pretty much count on your confidence interval to be useless. Because think about it. Any value between these would have not gotten rejected here in the null hypothesis. So the number we had here could have been as low as, say, 29.5% up to about 70.5%. Boy, that's a big range of intervals that would not get rejected. So it's not any big surprise that we failed to reject it. The power of this test is pretty lame and weak. So it wasn't until you did the confidence interval you realized, wow, I really need a bigger sample size because we do not have things narrowed down at all. And I realized how meaningless this conclusion was after looking at this confidence interval. So the next logical thing is, well, now, how large of a sample would be needed in order to have a margin of error? Now, let's see, what is our margin of error with this one? Well, let's just approximate it. So that would be 0.7056. Well, we'll go out 4 decimal places, minus 0.2944, rounding off. So that's the entire width, and your margin of error is half that. So if I divide this by 2, our margin of error is, about 20.5%. Boy, that's huge. Well, we would like to shrink that down to 4%. That would be a huge improvement. And let's have the confidence level at 99%. Well, now, looking at your formula sheet, let me move this over here. I don't want to get rid of all that writing there. So, which formula are you going to use? Well, let's see. You can't use this one because that's only for quantitative data. This is binary data. Okay, so it's between these two. Now, the question between these two, either you have a p-hat or you don't have a p-hat. Do you have a p-hat? I think so. You always have a p-hat if you've already done a hypothesis test. You know, that's our 16 out of 32. So you got to use this one right here. All right, then that's what we'll do. So I'll just do my work up here. And let's see, so let me write out my formula. And equals, I got my p-hat times my 1 minus p-hat. And you can just write z. You don't have to do that funny subscript if you don't want to. All right, so that's what we're going to do. Now, our p-hat is the 16 out of 32. Or if you put it as decimal, it's 0.5. I'm doing it as a fraction, just make it super clear you're following what p-hat is. And now let's see, what's our critical value? Well, if your confidence level is 99%, go over here, and that's your critical value. So that's what we put here, 2.5758. But you're familiar with this. You were doing this on your exam too. And then our margin of error is E is 4%. Now, how do I write that down here? You always have to have this in its decimal format. So convert 4 into its decimal format by taking this number and dividing it by 100. And that's 0.04. And of course, don't forget to square this. So now all we got to do is punch it on our calculator. So let's make sure we got the calculator skills. Left parenthesis, 16 out of 32. And that's times 1 subtract 16 out of 32. So yeah, looks good. And then we've got our 2.5758. That's divided by 4%, which is 0.04. Right parenthesis and then square. Now, how much bigger sample size do I need? Whoa, that's a lot bigger than 32, isn't it? Now, so let's go back to show our work here. Finish the job. So that does equal 1,036, and there's a decimal part to it, 7. And what we do is we round up, so even if that was 0.1, we would round up to the next whole counting number, 1,037. You're saying, wow. Now, if I had gotten a sample size of 1,037, I know we would have passed this test for sure. That's right. So not only would you have passed the test and this whole thing would be valid, but you would then have things narrowed down enough that you'd have a confidence interval that was meaningful. Also, you increase the power of the test, because this test had no power at all, because it was failing to reject a lot of values. If it was different from 37%, it didn't have the power to detect it. But as you increase the sample size, you're increasing the power of your hypothesis test to detect differences, such as being greater than 37%. Okay? So that's the idea. Whenever you have binary data, and so you're working on part 3, you always have to show the hypotheses. So you need to remember that, because your conclusions don't really make sense if you don't state what the null hypothesis or what the alternative hypotheses are. And you always have to show which parameter you're using, because I have to mark you down as much as the person who put in the wrong one, which in this case would be the population mean. So leave a blank, get marked down. Also, I expect you to show that you're checking conditions, because if you don't show it, I have to assume you're not checking. You didn't even think about it, and you have to be marked down accordingly. And after you check it, either you say the conditions are met or they are not, like are not here. And if they're not met, you still go ahead and do the work. Okay? All righty. So let's clear this one off. And let's take a look here at another one. Let's see here. What's going on with this one? A random sample of 25 subjects were administered a new diet. After 12 months, the sample mean weight loss was 1.6 kilograms with a sample standard deviation of 5.4 kilograms. Do these results suggest that the weight loss was statistically significantly greater than 0 at the 10% level of significance? All right, first, what are they asking for? Well, that's a hypothesis test. You know, that they suggest this, and notice the level of significance. Sure enough, that's only hypothesis test. It's either you go along with this idea or you don't. Okay, so you know it's a hypothesis test. Now, what type of data are we doing? So what are we doing to each one of these subjects? We're measuring how much weight loss they have. So that's quantitative data. Okay, quantitative data. So that means over here, you got to use the population mean. And you always have the equals, and the null means no difference. You know, that this diet made no difference at all. In other words, the weight loss was 0. Yeah, well, that's definitely no difference. So you got the 0 right from there. And then for the alternative, you copy down everything except for the equal sign. And they want to know if the weight loss is greater than 0. Because you're measuring how much weight was lost. They're saying, no, the diet's working. They're losing more than 0 pounds or kilograms in this case. Oh, before we go much further, should we check the conditions or should we just assume that they're met? Well, let's hope you don't assume that they're met. Well, let's see. What are the conditions for quantitative data? Well, let's do the first easiest one. It's got to be a random sample. We got that. What's the other? If it comes from a large sample size of at least 30. Do we have that? No, we don't. Is that so? Can we just stop there and say the conditions are not met? Don't do that. That's a common mistake. There's 2 ways this can work. You can have a sample size less than 30 if we know that the population is normal. Did they tell us that the population was normal here anywhere? No. So here's what we got to do. We need to make a note that the sample size was less than 30 and they didn't tell us the population was normal. Tell us the population was normal. So what does that mean? Conditions are not met. Oh, mind you throw an exclamation there. But if the population was normal, the conditions would have been met. So we'll just say that. But if, now notice this wouldn't make it, wouldn't apply in the world of binary data because populations aren't normal. In the world of quantitative data, they are. You do have a shape. But if the population had been normal, then this would have worked. or normal, we'll say, then this is what we would have done. And then we'll go ahead and do the work. Okay. So you're seeing both scenarios covered with binary data and quantitative data where the conditions could possibly not be met. And what to do about it. We're still going to show the work. Now here they're using a 10% significance level. So now on this one, they're making this really big. Now the only excuse you have for making this really big is if a type 2 error is much worse than a type 1. Because they're making, remember, this is the probability of a type 1 error. Look how big they made it. I mean, you don't want it that big. So they better have a good reason. And the only reason you would increase this up is to bring down the probability of a type 2 error, which is going with the null and being wrong due to sampling error. Hey, let's go to our little sketch here. So 0 is in the center, because in the center is always the number there. If you have a population mean over there, you got a sample mean over here. Now, if we land a little bit above, so as you go to the right, you're having more and more weight loss. Now, if it's just a little bit of weight loss, well, that's what you'd expect if the null hypothesis were true, which is what this is a picture of. But the farther to the right you go, the stronger the evidence is that the population mean is greater than 0. All right. Now, so if I were to land way off to the right, I'd go with the alternative hypothesis. Now, I could be wrong due to sampling error, and that's what a type 1 error would be. And they're willing to accept a big probability, 10% of a type 1 error, which is saying, hey, this diet, you're going to lose weight on it, and then you don't. Boy, that doesn't sound very good. And look, they're willing to make a big probability of that. Well, what is it they're afraid of? A type 2 error. What would that be? Well, a type 2 error is where we just land a little bit above, and so we do what we're supposed to do. We fail to reject the null, but we could be wrong due to sampling error, because here we're saying that, hey, you're not going to lose any weight on this diet. Don't bother with it. Oh, and it turns out we were wrong. You actually can lose weight on this diet, but we didn't catch it. A missed opportunity. Well, apparently, they don't want that to happen. Sounds like whoever were proponents of this diet are the ones who set the significance level. At least it certainly seems suspicious. So, well, that's what we'll work with here. Now, let's go over to our calculator and deduce which function we're going to use. So, stat and test. All the ones with the 2's, throw those out. Can't be one prob z-test. That's for the binary data. Throw that out. So, it's between z-test and t-test. Well, just like with z-interval, t-interval, we're always going to use the t-distribution because we're using the sample standard deviation. So, we're going to use t-test. So, let's document that. Make it clear to the world, this is a job for t-test. Then let's just go on in there and fill in the prompts. It'll prompt us for what it needs. Now, I'll have to highlight stats and hit enter if it isn't already selected. So this is your hypothesized population mean. This you get from the hypotheses, that's the 0. And then your sample mean. Now our sample mean was the 1.6. Now, make sure you have learned and remember what these symbols mean. Because if you don't remember what the symbols mean, you're going to really mess things up here. In other words, that you know, X bar is the sample mean, that's the 1.6. That's not the hypothesized population mean is 0. So don't get these two mixed up with each other. Because if you do, you messed up the whole thing. Now, our sample standard deviation is 5.4. And our small sample size is 25. And then we highlight the greater than, hit enter to select it. And then we highlight calculate and we hit enter. All right, now let's make sure we understand what all these mean. First, use this to verify you selected the correct inequality. We did, good, because if you select the wrong inequality, that will mess everything up. So it's important to make sure you got that. This is our test statistic, 1.48. So let's write that down and then put it in our sketch. So our sample mean, 1.6, that's above 0, but how far above? Well, just under 1.5 standard errors. That's right about there. So that's where our sample mean landed. So the question is, how unusual is that? Well, that's what this area from this point away from the center tells us. That's the probability of getting a sample mean this extreme or more extreme if the null hypothesis is true. So that area is your p-value. Tells you how unusual your test statistic is. And so that p-value is, I'll write as percentage, 7.57%. Now, you probably normally think of 7.57% as not being small enough to be considered unusual. But our significance level is a great big old whopping 10%. You say, oh my gosh, I am smaller than that. So that means your p-value of 7.57%, that's smaller than your great big significance level of 10%. So now you really want them to explain why is a type 2 error so much worse than a type 1, because it completely changes the conclusion whether this is 10% or 5%. So you start to suspect that someone's trying to pull the woolly over your eyes, that they really wanted this conclusion of to reject the null hypothesis and accept the alternative. In other words, saying there is sufficient evidence at the 10% significance level to support the claim that the weight loss is greater than 0, that you will lose some weight. Okay. But of course, we're willing to accept a 10% probability of being wrong about that conclusion. Well, I think one thing you definitely want to do is, okay, if it's more than 0, how much more than 0 is it? Well, that's why we're going to follow up with a confidence interval. Now, if you wrote down that you use t-test, just replace the word test with interval and you know what to use, t-interval. Why don't we go do that? Let's go over here, press stat, go over to test, go down here to t-interval, select it. Isn't it great when everything's already entered in like that? All you have to do is put in the confidence level. And I'm going to give that to you. We'll have to make this one 80%. So that's 0.80. And then highlight, calculate, hit enter. So we'll be 80% confident that the population mean weight loss on this diet will be anywhere, might be as little as, say, 0.18 of a kilogram to as much as a little over 3 kilograms. And so that's after 12 months of dieting on this diet. So each individual can ask themselves, so after 12 months and you only lost, say, 0.18 of a kilogram, would you consider that successful? Maybe yes, maybe no, but probably no. But you could also see how much it could be, a little over 3 kilograms. So at least you have an idea how narrowed down it is. But this was a small sample size. Now, here's the important thing. With quantitative data, you can have small sample sizes, and sometimes it's narrowed down enough. That never happens with binary data. You know, if your sample size isn't big enough to meet conditions, you can almost always count that your confidence interval is going to be far too wide to be useful. But that's not always the case with quantitative data, because with quantitative data, you can get things really narrowed down much more efficiently, far more efficiently than you can with binary data. It's just the nature of the beast of binary data. But let's suppose you do want to follow up with a sample size calculation. So what I'm going to do is, let me do a little erasing here. Let's see if this erases pretty quickly. Oh, not too bad. Because I want to roll this down. I don't want all this writing showing up here. Just getting most of it pretty efficiently. A few scraps here and there. Okay, so that got cleaned up pretty well. Now, let's scroll on up here. So we did that confidence interval. Now let's do a sample size calculation. So how large would the sample need to be? So I could shrink that margin of error down to 0.7 of a kilogram. And I definitely want to raise the confidence level, because that 80% was pretty low. So I want to raise it to 92%. Because you're saying now, if I could get things narrowed down this much, I'd be pretty happy. So let's go take a look at the formula sheet. And which formula are we going to use? Well, only one of them is for quantitative data. That's this one here. So that's the one you need. So let's go ahead and do the work. So, oh, by the way, this is where some people would get themselves in trouble. They say, hey, the conditions were met. I'm just going to leave it blank. Well, you can't do that with sample size, because the sample size always can get calculated. Because you know this is going to be so big that the conditions be met if you use one this size. So let's just write down our formula. And you don't need to do that subscript. You can just do Z sigma all over the margin of error E. And that's to be squared. So now if we're going to do 92%, and I believe that's what said, yes, 92%. We're going to go over here, and at 92%, our critical value would be 1.7507. So that's going to be multiplied by the standard deviation. And note that then we're going to estimate that with 5.4 kilograms. Now we're kind of fudging here, because really, when you estimate the population standard deviation with a sample standard deviation, it's only supposed to be done with a large sample size. So we are kind of fudging there a little bit, but that's all we got to work with, so that's what we're doing. But if you were to complain about that, I couldn't hold that against you. I'd say that is a valid complaint. 0.4. And all over the margin of error E, which is the 0.7 kilograms. All right, now all you got to do is punch that into our calculator. There's a decimal part, we round up. All righty here, so I got 1.7507. And I'm going to multiply that by 5.4. That's going to be divided by 0.7. Right parenthesis, and then square it. And that's a much bigger sample size than our 25. But that's what it'll take in order to get things narrowed down. So that's 182.4. And of course, we round up, because we have to meet or exceed these demands, to 183. Now, if we have a sample size of 183, would our conditions have been met? Yes, they would have. You don't need to know if your population is normal if you got a sample size over 30, and this is way over 30. And that's what you expect for the sample size calculation. It's going to be way bigger than what you need to meet the conditions. Because being 30 or more is enough to meet the conditions for the method, but it may not necessarily be big enough to get things narrowed down enough. That you don't know until you do your sample size calculation. And of course, this would increase the power of the test. You'd be more able to detect differences from the hypothesized value. Okay? So that's a nice little summary of what you'll be doing in part 3. So hopefully, if you have any trouble, you can refer to this and you won't have trouble anymore. At least that's what we're hoping for. All right, so let me go ahead and clear my drawings there. And so if anyone has any questions, I would go ahead and ask now before we close this session down. Trying to think here. Let me do this. If there were any other things I needed to mention, but I really can't think what those would be. So I guess without further ado, I don't see any questions. So that'll be it until next week. So have a nice long weekend, a holiday weekend. No classes on Monday. So we'll see you next time.